Hello, I am Tanwi Howlader and my student ID is 2022862216. This is the final report presentation of grid integration of energy systems, and the topic I am working on is a study on transient stability and voltage regulation within grid connected photovoltaic generation network. Grid integration of renewable energy systems refers to seamlessly connecting and managing renewable energy sources like solar, wind, or hydroelectric power within the established electricity grid infrastructure, ensuring their efficient and reliable contribution to the overall energy supply. The grid integration actually aims to optimize the flow of electricity from variable renewable sources by utilizing advanced technologies and control systems to maintain grid stability, manage the system fluctuations, and ensure a consistent supply of electricity to consumers. Balancing supply and demand dynamics is also an important goal of grid integration of renewable energy systems. It involves strategies such as energy storage implementation, smart grid management, and demand-side response mechanisms to balance the intermittency of renewable energy generation with energy demand, enhancing grid resilience and efficiency. So, what happens when we try to integrate our renewable resources to the grid? Grid connected photovoltaic systems offer many benefits but also face several challenges. Intermittency is one of them. Solar power generation depends on sunlight availability, causing output variations due to weather conditions, time of day, and season. Cloud cover, shading, or nighttime halt PV electricity generation. Grid stability is one of the issues. Fluctuations in power output from solar installation can affect grid stability, especially in areas with high solar penetration. Rapid changes in generation can impact grid voltage and frequency. The PV systems lack inherent storage, requiring additional infrastructure for energy storage or alternative power sources for the times when solar energy is not available. Dispatchability or the ability to control output is limited without storage solutions. Cost is one of the main factors when considering integrating the renewable resources to the grid. While solar PV costs have reduced significantly over the years, the initial installation expenses, maintenance, and associated infrastructure costs like inverters, grid connections, can still be a barrier to widespread adoption. Grid-connected PV systems must comply with grid codes and standards. Integrating them effectively requires synchronization with grid conditions to ensure reliability and safety. There are several technical challenges when the solar is integrated to the system. Issues like power quality, voltage fluctuations, and harmonics can arise due to the nature of solar power generation. These technical challenges need to be managed for seamless integration with the grid. Some factors like regulatory and policy hurdles, land use and aesthetics, environmental impact, and maintenance and durability are some issues that people face when they try to integrate renewable energy to the grid. There are several ways how we can mitigate the issues. Energy storage is one of them. Implementing energy storage solutions such as batteries can address intermittency problem by storing excess energy for use during low or no sunlight periods. This helps in providing a more stable and consistent power output. Advanced inverters and power electronics can also enhance grid compatibility and stability, allowing better control over voltage and frequency fluctuations. Microgrid and smart grid technologies that integrate renewable energy sources like solar or other generation methods, they can implement smart grid technology and can optimize power flow, enhance reliability, and manage grid stability. Hybrid systems that combine solar with other renewable sources like wind or hydroelectric power can help in balancing intermittency issues. This diversifies the energy mix and provides a more consistent output. Demand-side management and grid infrastructure improvement are also the way to mitigate this problem. Investing in grid structure upgrades such as better transmission lines, energy management systems, and distribution networks can accommodate higher levels of solar integration and improve overall grid stability. Also, encouraging consumers to adjust their electricity usage pattern through incentives or time of use pricing can help match energy demand with solar generation patterns. There are several requirements for implementing voltage control in grid connected networks. Analyzing the characteristics of voltage coupling, dynamic voltage control, transient characteristics of various interconnection in this system, coordinated management of distributed renewable energy power output systems, multi-step transient voltage are few of them. Current research has demonstrated that it is very important to take into account both the electrical coupling characteristics and the grid. It's critical to understand that electrical characteristics must be integrated with grid analysis technologies in order to completely comprehend a power grid's dynamic aspects. Dynamic voltage control is another requirement. It is essential to have clearly stated response mechanisms in place coupled with efficient distributed voltage controller coordination to provide stability, particularly voltage stability. Voltage instability and unnecessary regulations are avoided in this way. Through controller coordination, this is especially crucial in renewable energy systems with several devices, guaranteeing voltage quality and reactive power balance. The transient properties of distributed renewable energy stations, which include converter stations in both AC and DC systems, reactive power compensation equipment is examined for integrating renewable energy in grid. Conventional power system transient stability analysis techniques, including time domain simulation, power flow analysis, and the dynamic safety domain methods, are analyzed, particularly when it comes to grid short circuit problems. Coordinated management of the distributed renewable energy power output systems multi-step transient voltage is also a requirement. Power electric components such as PV units, wind turbines, converter stations, and reactive power compensation devices provide fast active and reactive decoupling control in distributed renewable energy power systems with both AC and DC output. Power electronic equipment's high controllability can be usefully utilized in a variety of failure scenarios. This controllability can be used to accomplish transient voltage cooperative control across different components of the distributed renewable energy power AC and DC transmission system. This is a basic block diagram of three-phase grid-connected PV system. Maximum power point tracking is implemented in this block. This block contains grid with inverter boost converter PV array with the control mechanism of perturbation and observation method and PWM method. This system can optimize energy, enhance efficiency, and they are also grid friendly. MPPT algorithm continuously adjusts the operating point of solar panels to extract the maximum available power from the solar array by tracking the ideal voltage and current combination, optimizing the energy conversion process. This system also enhances efficiency by dynamically adjusting the electrical power operating point of the solar panels. MPPT ensures that the system operates at its peak efficiency, maximizing the power output even under varying environmental conditions like changes in sunlight intensity or temperature. MPPT ensures that the power generated by the solar panels is efficiently and smoothly injected into the grid, aligning the output voltage and frequency with the grid requirements while maintaining stability and compliance with grid codes and standards. A typical configuration of a three-phase grid-connected PV system is shown in the slide. The equation for terminal voltage current characteristics is shown, where IPH is photocurrent, and V and I are the cell output current and voltage. The variables are as follows. T is the temperature of the solar array panel, K is the Boltzmann's constants, Q is the electron charge, and I is the reverse saturation current, N is the diode factor, Rs is the solar cell's series resistance, while Rsh is its corresponding shunt resistance. A PV array is made up of multiple PV modules coupled electrically in parallel and series circuits to produce the necessary voltage and current. The terminal equation for the array's current and voltage is given, where NP stands for the module's parallel number. Every module is made up of N series numbers and PV array cells. A flowchart of perturbation and observation method for maximum power point tracking is shown in this slide. The P and O method continuously perturbs or changes the operating point of a photovoltaic system, typically by altering the voltage, and observes how this change affects the power output. It increments or decrements the operating point to determine the direction leading to increased power. The flowchart also shows that by comparing the power output before and after the perturbation, the method detects whether the change led to a higher or lower power output. It literally adjusts the operating point until it approaches or reaches the maximum power point, where the power output is maximized. Simplicity and adaptability is one of the main reasons PO method is so popular. It's simple and commonly used in MPPT algorithm due to its ease of implementation and adaptability to changing environmental conditions. However, it can oscillate around the MPP under specific conditions, which may affect its efficiency sometimes in certain situations. A basic MATLAB model of a solar PV system implementing PO method is shown here. This Simulink diagram has a solar PV panel, a boost converter, IGBT switch, and diode. The voltage and current from PV goes through the MATLAB function which has the PO code, and it finally goes through PI controller. This is how the system works to implement perturbation and observation method. This slide shows the voltage, current, and gain curve of the solar PV system implemented in the previous slide. We can see that the PV current and voltage has some fluctuations in the beginning of the time, and then the PO method continuously tracks and keeps it in a stable point. After that, a MATLAB implementation of a 3-phase grid-connected solar PV system is also done. The system consists of 3 MW grid-connected solar PV system with PV panel of 319 volts and grid source is 400 volt with 550 Hz frequency. It also has a boost converter, a MATLAB function block which utilizes MPPT code, the inverter, and voltage and current control. First of all, to build this Simulink model, two constant values has been used for the solar PV panel. One is for irradiance, that is 1000 watt per meter square, and the temperature value is 25 degrees Celsius. This system has boost converter that consists 2 capacitors and 1 inductor, IGBT switch, and a diode. This section of the whole model gives the output voltage of the boost converter side. A MATLAB function block has also been used to implement the maximum power point tracking here, which uses PO method. The PV voltage and current are then connected to the MPPT function block. It's then connected to the PWM generator, which also provides switching pulse to the gate of the IGBT. In the inverter section of the model, universal bridge has been used to make the IGBT diode. 3-phase voltage measurement block has been used for the voltage and current measurement of inverter side. A three-phase source of 400 volt phase-to-phase and switching frequency of 50 Hz has been used. This model also consists voltage and current control mechanism. For the voltage control, output voltage of the boost converter has been compared with a fixed value constant. Then PID controller has been used to achieve a direct axis current value. The grid voltage is supplied to a PLL system to get omega value, which is utilized in the current control part of the system. While transforming ABC to DQ0 for current control, gain is divided by the voltage divided by the power. From the block, DQ value is taken. A sum block has been used to compare between reference current from PID and actual current from ABC to DQ0 converter. After the PID block, a voltage value is achieved and this value is converted to ABC value by the DQ0 to ABC converter. Two-level PWM generator is used during this conversion. Irradiation value for this model is 1000 watt per meter square. But if we reduce the value to 500 watt per meter square, this maximum power value significantly decreases and the change in grid side current is also noticed. This slide has two curves where the ABC frame voltage with respect to time when DQ0 to ABC is implemented is shown. Another graph has grid voltage and grid current shown. In this slide, inverter voltage and inverter current is shown. And in another graph, inverter power and grid power is shown. The power curves experience fluctuations at the first, but the control mechanism gives it a stabilized operating point after certain time. To conclude, it can be said that this study revolves around the voltage control method. It discusses perturbation and observation method for maximum power point tracking. This study demonstrated how, even in the face of shifting conditions, algorithms dynamically modify the PV system's operating point to optimal energy capture. Tracking speed and stability in grid-integrated photovoltaic systems is highlighted in this project. Reaching this balance is essential to maximizing energy output and extending system life. Significantly improved system performance, maximum power point tracking, and voltage control is achieved. These components directly improve the effectiveness, dependability, and viability from an economic standpoint of renewable energy solutions.